Okay, this is the computation loop. I am copying it, paste. Now, we need to start a loop, and the loop is extended over the simulation period. First of all, this code allows you to start not from for whatever position in the simulation period. So if you want to start your simulation not from time 1, not from the first hour, but from the hour that is located at the position 4000, you can do it by defining a variable sk, which is defined here as equal to 4000. My suggestion is to change this value to 1, because our first application will be to the whole period. And then the loop is extended, you see, it's a 4 cycle. The 4 cycle is extended from I is the variable of the cycle. I think you already have had some experience with cycles in whatever language. And a cycle is a repetition of the same instruction. What we need to make here is a repetition to each time step of the model equations, of the computation of the discharge. It must be repeated, same equations repeated at each time step. And therefore a cycle is the proper way to do it. And the cycle is defined through a cycle variable. And the usual symbol for the cycle variable is I. So I will vary from sk to n delta t. And this is the way in which you should write cycles in R. I propose to you to make, because I think we already made a cycle in the application of the linear reservoir, so you know it. You already have some experience, okay? So this is our cycle, and then I need to open a parenthesis for the cycle. And look, at each time step, I need some explanation for the first instruction. You see W1 equal to W2. First of all, I define W2, but I didn't define W1. W1 is indeed defined here. So this is acceptable in R. Some languages need that all the variables are defined beforehand. So you could also define W1 in the previous instructions by setting W1 equal to 0. In this case, I opted for defining it here. But why this instruction, W1, W2? Because we are at each time step, you may remember, we start with the initial value of W, which is the storage in the catchment, and at the end of the step, yes, we update it, and we compute the value of the storage resulting from what? Resulting from rainfall, which increases it, and resulting from evapotranspiration that decreases it. So at the beginning of the time step, we start with W1. So we have our time step, which is 3600 seconds. Here we start with W1, and then we have during the time step PT and ET. And the runoff. So let me call it ERT. So at the end of the time step, we end up with a different storage. And they are different because we are working on finite time steps. So we need to work with two values of storage at each time step, the initial and the final. So the first instruction is, let me set, and keep in mind, the final value, W2, of this time step when we move to the next step, which is this one, here we get W1 again, which is the W2 of the previous time step. So, as a first operation in the time step, we need to set W1 equal to W2. And this is why there is this instruction. So the first instruction is just to say, look, my W1 is equal to the previous W2. Okay. Now there is the computation of C1, which is the C value, the value of C that you have at the beginning of the time step. And this equation is the equation of the Hydrology model that allows you to compute C. If you look back at the relationships that I provided to you for the computation of C, it is this relationship here. Okay. So, keep in mind that this C1 is computed depending on what? W1. You remember that there is a relationship relating C to W. And this is the relationship that I'm using here. So at the beginning of the time step, I set W and I compute C. Okay. And then what happens during the time step? I have rainfall, which changes the C, and evapotranspiration. So you see that the third line, this one, is simply adding rainfall, but you see that C2 is equal to, forget about the minimum for now, C2 is equal to C1 plus rainfall. P is the symbol for rainfall. Be careful that the application of this function will require that your rainfall is stored in a vector which is called P. Be careful of that. Okay, so probably you need to change the name of the rainfall vector. So, as I said, forget about the minimum. You see that C2 or C is updated by adding to the C1 value the rainfall. But we have to make sure that we don't exceed Cmax. We cannot exceed Cmax. You remember that C has an upper limit which is Cmax. So this is why I put a minimum function there, which basically says if C1 plus P is greater than Cmax, then take Cmax through the use of the min function. Now there is the computation of ER1. Remember that ER1 is different from 0 only if we get complete saturation over the catchment during the time step. And this relationship that I'm now highlighting is what I gave to you for year 1. It's the maximum between C1, C, plus rainfall, minus Cmax, and 0. Okay, and now we have W2. What is W2? Remember, we updated C by adding rainfall. So given that W and C are directly related, I can compute an updated value of W. And this updated value is what I want to compute at the end of the time step. So I started from W1. Now C was incremented through rainfall, so let me compute the corresponding W2. And keep in mind that we will need to subtract evapotranspiration after that. But let me make a first step to compute the new value of W after rainfall. And this is computed through this relationship. Again, this is the relationship of the IMOD model, which is the reciprocal of this one. This one, which I'm indicating with my finger, is the one that gives me C depending on W. The reciprocal is the highlighted relationship, which allows us to compute W depending on C. Perfect. And now I can compute ER2. And look, ER2 is computed before subtracting evapotranspiration. This is just a personal choice. As I said, this is numerical approximation. So basically ER2, again, the same relationship that I explained to you yesterday. You see, C2 minus C1 minus W2 minus W1. And there is just a check that its ER2 is not lower than 0. It's probably a check that it's not necessary, but sometimes, in the algorithms, it's better to put some checks because it may happen that after numerical integration, you get some mistakes. After numerical approximation, you get some unrealistic values. So a contribution to runoff cannot be negative, and therefore it's better to make a check. And the same check was put here for year 1, because implicitly we make sure that year 1 is greater than 0, or equal to 0. The same here. Okay, now there is the next line, which is, yeah, please.
Maybe I just missed it, but what is EP?
EP is the next one. Computation of evapotranspiration is here. As I said, it's subtracted after computing the surface runoff. You may decide to subtract it before than that. Doesn't change much. It's numerical approximation, so the order matters a little bit, but shouldn't matter much if the time step is short. Is this clear?
EP is not previously defined, right?
EP is it's like rainfall. It should be already in your memory as a vector. Okay, because as I said before, you have to make sure that before running this program, that you have the input variables already stored in R. And the input variable are rainfall, evapotranspiration, and observed discharge. So we need to make sure, he anticipated my recommendation, to make sure that we have a variable called EP, which is a vector, not a variable, a vector containing all the data of evapotranspiration, which we need to upload from the file, from the data file. Now let's move to the next line. This is, depending on the EP value, this is the computation of the effective evapotranspiration. Again, this is the relationship that I gave you yesterday for computing the effective evapotranspiration. And now we can subtract evapotranspiration from W. And again, we need to make sure that W remains positive. So basically what I do is to define a new W value by overwriting the previous one, and the new value is obtained by subtracting from the previous W value, from the previous W2 value, the effective evapotranspiration. You see that it's, forget about the mass for a moment, it's W2 is equal to W2 minus E. And then there is the max function, which is a check to make sure that the result is positive, is basically non-negative. And now the last line is just the sum of year 1 plus year 2 to get ER, which is a contribution to the surface runoff. Okay, I think we can move to the next block of instructions, which is the routing, the runoff routing. Let me take this group of instruction, I copy them, and I paste them here. So my last, if you look above, my last instruction was the computation of the sum of year 1 plus year 2. And now I need to subdivide this contribution in quick and slow contribution through alpha. So basically you see that the quick part of year 1 is given by alpha times year 1. Times ER, sorry. The slow part of ER is given by 1 minus alpha times ER. This is very simple. And now let's compute the slow flow. And this is just an application of the linear reservoir. And this application is very compact, just 2 lines for applying a linear reservoir, but it's not so easy to understand, so I want to explain to you why these 2 lines. So let's look at the first one, which is easier to understand. So basically what it says, I'm copying, it's W. Let me drop slow, because let's assume as it is that we refer to the slow reservoir, so I don't need to copy slow anytime. So it says W is equal to 1 minus K times W, and plus times U is, let me just use U, is the contribution to runoff. So remember that U is what enters into the reservoir. So basically, here I have UT, and I have a water content which is WT, and then I need to compute this result here, which I don't remember how it's called. It's called Q. Perfect. So basically U is our previous rainfall, let's say. So let me rewrite it by taking the multiplications here. W is equal to W minus KW plus U minus KU. Okay? So basically what it says is W is equal to the previous value of W minus what outflows, because it's the computation of the linear constant times the previous value of W. So it's basically saying that W is equal to the previous value minus what goes out, and rainfall is still not taken into account here, plus rainfall, which increases the W value, minus what goes out, because while it rains, W increases, and part of the rain goes out from the reservoir. So I need to take it into account by multiplying K times rainfall. So this is different from what we used before, because in our exercise we first added rainfall to W, and then we computed the outflow. So it's written in a different way, but it's the same thing that is done here. Because, you know, it's like I could write it in this way. I could write it as W plus rainfall, W plus U, minus K, which multiplies W plus U. So this is the way in which we used it. The new W is equal to the previous value plus rainfall minus the outflow. It's the same writing, but it's written in a different way. And in order to make the understanding of the next relationship easier, let me write this by distinguishing the new value of W from the previous value. So let me call this W2 and this one W1. Because these are different. The program doesn't make any difference because it is overwriting. But in order to make clear, again, the understanding of the next line, let me put in evidence that they are different values. Okay. And then let me keep only this relationship here. Or maybe, let me see. Let me keep all of them. W2 is equal to W1 minus K W1 plus U minus K U, and W2 is equal to W1 plus U minus K W1 plus U. Let me keep all of them. Now let's move to the next one. The next one is the computation of the outflow. So let me write Q. Q is equal to K divided by 1 minus k times W2, because I'm using here the new value of W, so let me use 2. This is something that you may not understand. Indeed, it's easily understandable, and in my opinion could be also more easily written in the code if you substitute for W what is given by this first relationship. So let me substitute for W this one. So Q is equal to K, 1 minus K, which multiplies 1 minus K W1 plus 1 minus K U. At this stage, you easily see that the 1 minus K goes out, and we remain with Q is equal to K W1 plus U, which is what we would expect. So we start from the previous value of the volume. We add rainfall, multiply by K, and get Q. This is what we did in our linear reservoir. So that's fine. And, but here it's written in a more complicated way. Why is that? Because they wanted to use less variables. So here you have only one variable for W. Instead, in order to explain to you, I had to introduce 2 variables. And therefore, the programmer thought that this is simpler and also is requiring less memory from the PC. And in turn, it means that the algorithm is faster. So this is why he decided to write it in this way, but it's not so easy to understand. It's smart, I mean, because you see that with only 2 lines, he routed U, which is equivalent to rainfall in our previous case, through the linear reservoir. It's smart. Okay. Now the next block, which will be the routing through the 3 reservoirs, the sequence of 3 reservoirs. So let me take here quick flow. And I think we can copy up to the comment drawing the block, because here the next set of instruction is very easy. So let's copy the root bit, copy, and let me copy it here. The quick flow, and here there is a variable that is defined, and let me see, it's not strictly needed. It's not strictly needed that you define it here. I think the best thing would be not to define it here, but to define it in the block where we define the variables, in order to define the variables all together. Okay? So, if you wish, for clarity, you can bring this definition up. And then, you know, here there is the same set of instructions that we used for the slow flow, with the difference that there is a cycle which repeats the instruction 3 times. And another difference is that is given by, if you look here at these lines, here you have a 4 cycle, which is fine. This instruction is the same that we used before for the slow flow, and even this one. These 2 are the same instructions that we just used. The only difference is here is that W is not a variable. Now it's called W quick. It's not a variable, it's a vector, because the reservoirs are 3. So W quick needs to be split into 3 values, 1 for each reservoir. And then there is another instruction that is needed here to substitute the inflow to the next reservoir with the outflow from the previous one. This instruction, which was not needed before, says that U at the next step is equal to Q at the previous step. So the discharge from the previous reservoir is equated to the inflow of the next reservoir. And then there is the closure of the fourth cycle. And what you get at the end of the story is a Q quick, which was routed through 1, 2, 3 reservoirs. And then what you need at this stage is just to take the sum of the slow contribution plus the quick contribution and multiply it by the conversion factor. And the last parenthesis is the closure of the simulation loop, which is repeated 87 and 60 times. So basically at this stage we are done. The only thing that we need now is to produce the plot and maybe to give back Qt as a vector to R if we want it. But the application of the model is finished. And look, if you look at this algorithm, it is extremely simple. We took more time in explaining the theory, definitely more time. And I think also more time in understanding the theory than the time that we took to explain the algorithm and how it works. I am assuming that you understood everything of this algorithm, but I'm sure that you are not far from that. Maybe that you have some doubts, and maybe the doubts are related to this. Because, I understand that this application of the reservoirs in sequence is something that probably you need to think a little bit about. But it's very simple. Okay, and now let me go back to the website to get the final instruction, drawing the plot. And here there is nothing to say. Basically, the plot is extended to the part of the time series that we simulated. And there is an adjustment of the scale of the y vertical axis in order to adjust the scale depending on the simulated values. And then there is the superimposition of the observed value. And the simulated one is in red, the observed one is in black. And here you see that there is a first instruction that is commented, which is a cut instruction. Cut means output to the screen. This cut instruction, which I commented out, has the purpose of displaying to you the tentative value of the parameters if you want to see them. This may be useful because it may be useful for you to see what the routine is doing. So the values that the routine is trying. I commented it out because we don't need it now. And then the return instruction, it's an instruction that tells the function to give back some variables. Remember that all the variables that you are using into the function are not kept by R. They are cancelled out after the function is finished. And this is a smart decision because, you know, it's a way to keep the memory clean. But if you want that some variables are kept, you have to use the right of instruction. And here we have two options. One is commented out, which is the simulated flow. And I decided to give back only the sum of the squares. What you see here is the computation of the sum of the squares. And I decided to give back only this one because this is the output that the optimization routine needs. The optimization routine needs the sum of the squares to minimize, to apply the least squares estimation. And that's it. So, given that the code is finished, let me save it. And imo.r, and let's try to launch it. In my case, I need to upload the data, and I will try to be very quick. Probably you don't need to upload them because you already have them. But if you want to follow me, of course, you are welcome. First of all, I need to get the data from the website, and here I have the link for rain and evapotranspiration. Let me get it. Not sure if